This video will be about the future of artificial intelligence, machines, robotics, and programming in the future of warfare. The primary source is Paul Scharre's Army of None. Hopefully, we will be able to determine a doctrine surrounding AI warfare that maximizes the following of international laws of war, while still creating a highly effective tool for defense. Part 1. Robopocalypse Now. The first step is to look at existing automated and computer-controlled weapons currently in use. For examples of this, we have plenty of experience from the US military's campaigns and bombings in Syria, Iraq, and Afghanistan. Predator and Reaper drones, which have participated in bombing missions in Syria, Bosnia, Pakistan, and Iraq, are still flown manually, remotely from the ground. Other aircraft, such as Air Force Global Hawk and Army Gray Eagle drones, have more automation. The pilots only direct these aircraft. It is telling about the amount of automation and computer control that the US Army refers to the people controlling its drones as operators rather than pilots. The term pilot would seem to confer more control than the Army gives to its operators. As time has progressed, engineers have been incrementally adding to the set of tests uninhabited aircraft can perform. The X-47B drone made history by conducting the first autonomous aerial refueling, taking gas from another aircraft while in flight. Swarming can also allow militaries to field large numbers of assets with a small number of human operators. Their programming relies on cooperative behavior to prevent crashing in each other, and to prevent overlap in mission commands. Cooperative behavior can also allow quicker reaction times. Swarm dogfighting experiments have been conducted by Davis and colleagues at the Naval Postgraduate School, which push the boundaries of autonomy. However, swarm tactics are still at a very early stage. The Terminator and the Roomba. What is autonomy? The second step of analysis is then to determine how autonomous robots can be, what advantages autonomy can confer, and how autonomous should robots ethically be. But first, I will define autonomy. Oxford defines autonomy as freedom from external control or influence, independence. Autonomy for robots can be considered as how separated from human control the robot's actions and decisions are. A very limited autonomous system will usually take the orders from a human, like a human selects a target with the robot's vision, and then the autonomy guides a missile until contact and explosion. However, a human remains in control to deactivate the attack at any time. A fully autonomous system will sense, decide, and act entirely without human intervention. Humans are out of the loop entirely, outside of the broad power to take the robot out of a mission when they deem the task accomplished. Autonomy's progression can be simplistically modeled on this figure here. At present, often a single machine will perform some tasks autonomously while humans are in control of other tasks. For example, if a pilot becomes disoriented and is about to crash, Auto Ground Collision Avoidance System, GCAS, will take control of the aircraft and pull up to avoid the ground. This has rescued an F-16 in Syria. Automated systems are more complex and consider a range of inputs and several variables before taking action. With most systems, these variables can be easily tracked and monitored to understand the machine's thinking. However, with the neural nets that have many deep layers and systems that track countless different variables, the ability to understand the system's thinking and process becomes far more difficult to humans. This becomes extra important when humans have to program machines to understand out-of-action troops, which we will discuss later. An example of very limited autonomous systems are smart missiles, also called smart bombs or precision-guided munitions, PGMs. PGMs use automation to correct for aiming errors and help guide the munition. In other designs, a human operator paints the target with a laser or radar to guide. Other PGMs are autonomous in the sense they cannot be recalled once launched. Homing is not very autonomous because a human decides which specific target to attack, and the autonomy simply determines which way to turn and how to maneuver to hit the target. This concept is also talked about in my fighter weapons video. The role of autonomy is simply to be a better steering wheel in this case. Part 2. Building the Terminator. A handful of experimental programs shows how the US military is thinking about the role of autonomy and weapons. It is currently difficult to teach machines how to maneuver around even basic obstacles at slow speed. So many different programs are springing up to solve various problems like these. One example of this is GRASP, the General Responsibility Assignment Software Patterns, and another is the Collaborative Operations in Denied Environments, or CODE program. These programs are working to engineer unmanned aircraft like fighters that work together. 10 different fighters could work under the supervision of a single person in the future. This works especially well with the US 5th Gen fighters that have lower chances of interception and detection. In Ballston, Virginia, is a nondescript office building with a marble wall that proudly proclaims Defense Advanced Research Projects Agency. The simple aesthetic and basic signage may have you believe that it is an ordinary building with normal government workers, but make no mistake, the future is being made here by a department of mad scientists. DARPA was founded in 1958 in response to the strategic surprise of Sputnik. American strategists and politicians were determined not to be caught off guard again by the Soviets or anyone else, and if possible, they were going to achieve the surprise against the enemies of the United States. DARPA is organized into 6 departments: biology, information science, microelectronics, basic sciences, strategic technologies, and tactical technologies. The Tactical Technology Office builds experimental vehicles, ships, airplanes, and spacecraft. One example of their work is the entirely unmanned ship for anti-submarine warfare called the Sea Hunter. DARPA's fundamental mission is unchanged: enable early investments for breakthrough capabilities for national security and prevent strategic surprise. Militaries will need more autonomy as warfare grows more complex in situations where electronic warfare threatens communications with humans. Having a human involved in a monitoring role still implies some degree of connectivity, which might be difficult in a contested environment with jamming. Autonomy makes weapons more resilient to communications disruption. For example, if you can imagine a Raspberry Pi or a Arduino on an autonomous drone, it will not require any independent signals to keep its running going if it can independently find targets with a camera and then fire at them with any onboard weapons systems. So the question becomes, to what degree should humans be able to interfere with machine decisions? Delegating lethal decision-making comes with risks. For example, what if autonomous software enabled a swarm to execute a mission against the wrong target? This scenario implies some necessary amount of control and oversight from actual humans. When flaws are created in programs which are copied in all models, the flaws are likely to be replicated in entire squadrons and fleets, leading to incidents of mass lethality. This phenomena of mass lethality from copied errors is fundamentally different from human mistakes, which tend to be individual incidents. Now that we're worried about machines choosing the wrong target, we should consider how machines find targets in the first place. Military targets can be grouped into 2 categories: cooperative and non-cooperative. Cooperative targets actively make a signal, making them easier to detect. Enemies looking to target and destroy the enemy can simply home in on the source of electromagnetic energy. This is how autonomous weapons like the Harpy find radars. They use passive sensors to wait and listen for cooperative targets, broadcasting their position. Non-cooperative targets don't broadcast location. These could be ships or aircraft with radars turned off. The military's current technique for spotting non-cooperative targets is called synthetic aperture radar, or SAR. A vehicle flies in a line past the target and sends out a burst of radar pulses. This creates images composed of small dots. But how does a computer know what is in that image, or how to determine an enemy from within that image? The answer is deep learning from a training set within the framework of a multi-layer neural network, and an optimally determined set of output possibilities, which are essential for image recognition. If you know what that means, you can skip ahead to here. If not, I'll explain it now. You know how all those "Are you a robot?" tests where you pick out a traffic light or a traffic sign? The truth is that they don't test whether or not you are a robot. Ironically, the point of those tests is to teach robots how to pick out traffic lights and signs. With many people sorting signs and lights from images, there is now a giant set of tests that programmers can give to programs. These are called training sets. The neural networks computers think with are composed of various biases and multipliers that convert the many input values into probability output values. A large set of different neural nets with the same structure but different multiplier and bias values are then created. These nets then test themselves with the training set. The best of the performing nets are kept and edited slightly, creating a new generation of neural network designs. The cycle of testing and recreation is then performed again with the new generation until a highly accurate neural network is created. This process of testing and recreation is called deep learning. The middle bubbles in the structure of the neural network are called hidden layers. With many hidden layers between input and output, you have a multi-layer network. Back to robots in warfare. With this process, engineers have created small drones that can find crashed helicopters and other entities on their own, and report the location back to humans. DARPA's TRACE program has been the driving force behind AI advancements in deep neural networks. They've been taught to win at Atari, Go, perform speech recognition, and visual object recognition. As I record notes for this video, I'm using Speech Texter, which has AI create text from the words I speak to it. I can affirm that it is pretty accurate. The tools used to train Go and chess are generalizable tools that can be used to build any number of special purpose AIs. One great source for this is TensorFlow. TensorFlow makes neural networks easy and fun. A tutorial called Playground at tensorflow.org allows users to modify and train neural networks through a point-and-click interface. ImageNet is the only visual object classification database. These softwares can determine human faces or label human emotions from massive databases in 10 seconds or faster. Sun Tzu wrote over 2,000 years ago in The Art of War that speed was the essence of war. Human decision-making has advantages over machine intelligence, but is not nearly as fast. Stock trading is a field in which many models have been tested, and there has been constant competition for faster algorithms to shave microseconds off reaction times. However, there can be accidents from this. Flash crash. May 6, 2010 at 2:32 p.m., the S&P 500, NASDAQ, and Dow Jones lost 10% of their value in 13 minutes. And yet by 3 p.m., the glitch was over, and the markets had regained their value. Nightmare on Wall Street. In 2012, Knight Capital Group executed 3.3 billion trades, totaling $21 billion per day. This was about 17% of all trades on the New York Stock Exchange and NASDAQ. Sounds awesome and profitable, right? July 31st, 2012. $365 million in assets lost. Bankrupted in 45 minutes, faster than a game of Monopoly. The program failed to record the completion of smaller trades, and so it flooded the market with orders for trades, raising up the price, continuously buying and selling at a loss. No off button. Imagine a program moving $2.6 million every second. After 45 minutes, the program had moved $7 billion at a net loss of $460 million for a company worth only $365 million in assets. In science fiction literature, there is a theme of artificial humans rebelling against their makers. Frankenstein, Blade Runner, and Terminator come to mind. And you can see in the stock exchange an example of where trusting technology has caused doom and destruction for certain companies. Current law and the possibility of restriction. The Department of Defense Law of War Manual states that laws of war impose applications on persons, not on the weapons themselves. This means that from the DoD's perspective, machines, even intelligent autonomous ones, cannot be legal agents. They are always tools in the hands of people. Foreign perspective. International humanitarian law has 3 core principles: distinction, proportionality, and avoiding unnecessary suffering. Distinction means militaries must distinguish between enemy combatants and civilians. Proportionality says that any collateral civilian casualties cannot be disproportionate to military necessity. Avoiding unnecessary suffering prohibits militaries from using weapons that cause superfluous injury beyond their military value. The first two principles create problems for AI warfare. With distinction, it is harder to distinguish non-cooperative targets who don't emit radar or use camouflage. This is a problem when robots must determine counterinsurgents from civilians when they are in the same area, look alike, and dress alike. Modern urban environments are rife with electromagnetic signals from Wi-Fi routers, cell tower televisions, and radios, after all. With proportionality, a computer system that controls many systems may calculate an increase in military damage, but will only consider cost in terms of the amount of missiles used, not considering the value in sparing civilians from destruction. However, automation also provides a moral buffer between humans and the consequences of their actions. To quote a former F-18 pilot, "It is more palatable to drop a laser-guided missile on a building than it is to send a walleye bomb into a target area of the live television feed that transmits back to the pilot in real time images of people who, in seconds, will no longer be alive." In 1947, U.S. officials worried that the scale of nuclear weapons gave an advantage to a first strike. This dangerous dynamic captured what theorists called first strike instability. Instability refers to any situation that will undermine the current status quo militarily, which in our case is peace between the great powers. In some cases, defensive weapons can also be destabilizing. National missile defense shields destabilize because they undermine the viability of an ensured second strike. If you are interested in the concepts of strategic analysis, especially related to stability and instability, I can cover it in detail in the book Thinking About America's Defense. Comment below if you want to hear this. Autonomous weapons risk accelerating the pace of battle by shortening decision-making time, thereby destabilizing the peace. Crises are rife with potential for miscalculation when speed is critical. However, AI weapons are stabilizing in the sense that they cannot violate their orders. A wayward general looking for glory can order soldiers to fire, but AI can be programmed to not fire without authorization from multiple sources or only the highest authority, the president. In the 1964 film Dr. Strangelove, an excellent movie by the way, go check it out, explores the bizarre logic of deterrence and mutually assured destruction. In the movie, the Soviet Union builds a doomsday device which, if the Soviet Union is attacked, will automatically explode a series of nuclear bombs that will irradiate the entire surface of the Earth, making it uninhabitable for humans. The Soviets did actually build a real-life automatic doomsday device nicknamed Dead Hand, officially called Perimeter. It was an automated nuclear command and control system, allowing a massive retaliatory attack if a US first strike took out Soviet leadership. So that's fun, right? However, if nuclear weapons were fully restrained or if they were destroyed, their value as a deterrent would be lost. After all, there has never been a direct war between nuclear powers. The devastation of a nuclear war was expressly given as the reason leaders of both powers were determined never to go to war with the other. Chapter 20 discusses the history of weapons bans. Whether a ban succeeds or not seems to depend on three key factors. 1. Perceived horribleness. 2. Perceived military utility. And 3. The number of actors who need to cooperate for a ban to work. Now to wrap it up with a warning. China has launched a national-level AI development plan by increasing research investment into AI and aggressively recruiting top experts from Silicon Valley. Data is central to machine learning systems, and Europe's new data privacy laws are pushing out companies from access to user data, which could otherwise help train machine algorithms. So there are many possibilities as to what the future holds for AI warfare. Will China take the initiative and build the strongest army in the world? Will the US be able to maintain its military superiority and continue to police the world? Could the French or Germans emerge as new superpowers through these technologies? Remember, the future is in your hands.